We left off our last video talking about how we wish we had better techniques for finding the zeros of polynomials. Up to this point, we've seen it either had to already be factored, or we kind of got lucky with a good guess, but hey, we know real numbers in the real world aren't always really pretty. So we'd like to have some other techniques for helping us find the zeros of a polynomial. That's what we're going to look at in this section. One of the things we are going to use for that is the rational zeros theorem. So that's the first objective. Use rational zero theorems to find possible rational zeros. That word possible is really important. It doesn't give you zeros, it gives you maybe zeros. And then once we have those, we are going to find zeros of the polynomial function, solve polynomial equations, which is similar, and then write a polynomial given its zeros. I wanted to start with a little bit of motivation. Why would we want to do this? So here's an example that may help us sort of see what we're trying to get at here. A popular model of carry-on luggage has a length that is 10 inches greater than its depth. Airline regulations require that the sum of the length, width, and depth cannot exceed 40 inches. These conditions, with the assumption that this sum is 40 inches, can be modeled by a function that gives volume of the luggage v in cubic inches in terms of its depth, x in inches. Part A says write this volume function. All right, we're talking about luggage here, so we're in 3 dimensions. I am going to just sort of create this 3-dimensional, piece of luggage here, handle on top, whatever, right? Okay. Its length is 10 inches greater than its depth. So I'm going to call this depth x. Is that what it says here? Yeah, its depth is x. If its length is 10 inches greater than that, then this has to be x plus 10. And then we have length, width, and depth. So I guess I've kind of got the height is really what we have missing here that I'm calling width here, I guess. It's the only one I haven't used yet, right? So let's call that y for the moment, okay? The regulations require that the sum of the length, the width, and depth cannot exceed 40 inches. So let's say x plus 10 plus x plus y is equal to 40 inches. That means 2x plus 10 plus y equals 40. If we subtract 2x from both sides and we subtract 10 from both sides, we get 30 minus 2x, I think is what we'll get there. If we subtract 2x, subtract 10, I'll put that minus 10 here. So there's the 30, 40 minus 10, and then minus 2x. So instead of writing this in terms of y, I'm going to write this in terms of x, 30 minus 2x. Now we know volume of a rectangular prism here, or a rectangular box here, is length times width times height, right? So in this case, we are going to say it is x plus 10 times x times 30 minus 2x. We have to measure those dimensions. So this volume as a function of x can be written that way. Well, that's nice because that's in factored form, and so if we needed to solve that, set equal to 0, we could do that. But setting that equal to 0 is kind of strange because that's saying the volume is 0. That's not really what we're going to want to do. What we want in part B, this is part A, answer to part A, if the volume of the carry-on luggage is 2,000 cubic inches, determine 2 possibilities for its depth. Round to the nearest tenth of an inch. So I just want that volume to be 2,000. Okay. Determine two possibilities for its depth. Okay, well, we're in a little bit of a hard part here because you can only set factors equal to 0 if in this case, the left-hand side is equal to 0. So that is not going to work. We are going to have to multiply this out. First, let's distribute that x into the x plus 10, and then we'll distribute out the right-hand side of this. We have 30x squared minus 2x cubed plus 300x minus 20x squared is equal to 2,000. Now, if I want that side equal to 0, which is usually the easiest way to solve a polynomial equation, and then put it in descending order, I'm going to get negative 2x cubed plus 10x squared, when I combine those two like terms, plus 300x, that puts that in descending order on the right side, but I also have to subtract the 2,000 from both sides of the equation. So I get this equation, so this is pretty key to what we are doing here. The problem is that that's not in factored form, and we can only set factors equal to 0. And so we could do what we tried in the previous section where we try some guess and check and see what works. But I think let's wait after we learn some better techniques. We may have better luck at our sort of guess and check, especially because these numbers are kind of, you got some big numbers going on there. So we'll come back to that. The rational zeros theorem I mentioned above gives us possible rational zeros. We're going to focus on this last term, a0. We want all the divisors of that. We're also going to focus on the leading coefficient and find all the divisors of it. And then we're going to put those in a ratio, divisors of the a0, which is the constant term, over divisors of the a sub n, or the leading coefficient. And those will be our only possible rational zeros. Any rational zeros must be of that form. They cannot be anything else. That narrows down our guess and check, right? Let's try it with this one. P is going to be divisors of the constant, which in this case is 6. And Q will be divisors of the leading coefficient, which in this case is 2. Divisors of 6, that's anything that divides 6. Well, 1 will divide 6, 2 will divide 6, 3 will divide 6, and 6 will divide 6. So will the negatives of all of those. When we say divisors, we're talking about things that will divide it evenly. If I divide 6 by 3, I get an integer. If I divide 6 by negative 2, I get an integer. So I'm just going to put a plus minus in front of each of those. So I actually have 8 total divisors of 6. When I do the same thing for 2, it's just positive or negative 1 and positive or negative 2. That means my possible rational zeros must be of the form P over Q. So I'm going to take each of these and put them over 1. Well, anything over 1 is just itself, right? So I get each of those divisors of 6 over 1. If I put them over negative 1, I get the same things. It would just be the opposite order. It would be minus over, minus plus instead of plus minus. So I don't need to rewrite these first 8 that I have listed here take care of these over the plus or minus 1. Now I need to take care of those over the plus or minus 2. So let's do that. So 1 over 2 is going to give me plus or minus 1/2. Then I'll get plus or minus, if I do 2 over 2, well, that gives me 1. So that I don't need to rewrite that. 3 over 2 gives me 3/2. And then the last one, 6 over 2, would give me 3, which I already have written here. So I don't need to rewrite that. So these are all of my possible rational zeros. Going forward, you'll probably see me abbreviate this possible rational zeros, PRZ. Okay? For some reason, that makes me think of PVZ, which is language in my house a lot because I have an 8-year-old, Plants vs. Zombies. He loves that on his Xbox. So we hear, Mom, can I play PVZ? All the time. Okay, those are my possible rational zeros. We are going to do that again here. We've got a different polynomial, but the same idea. P is going to be divisors of the constant, which is 7. Well, 7's a prime number, so only 1 and 7 divide it. And then, of course, the negatives will divide it to give you an integer. And Q will be divisors of the leading coefficient, which in this case is 1. One thing you need to make sure of is make sure it is in descending order. Because if it's not, then your Q will be divisors of, if this had been to the 9th power here instead of the 3rd power, it would be divisors of 3 that I was looking at. In this case, 1 is the only divisor of 1. Divide that evenly. So that means my possible rational zeros are, well, we put each of those over, each P over each Q. You put 1 over 1, you're going to get 1. Put 7 over 1, you're going to get 7, and that's it. This is a super small list. It's only 4 total possible rational zeros. +1, -1, +7, -7. That is super helpful if one of those works. So we have this sort of celebration over here because we have narrowed down our guess and check list. These at least are rational, possible rational zeros. There is absolutely no reason to try x equals 2 as a zero of a function, of this function. It will not be. The problem we run into is what if you have irrational numbers, irrational zeros. So this just helps us with rational zeros. Remember, rational numbers are ratios of integers. So we are talking about integers or fractions that have an integer over an integer. Like up here, 1/2 is a rational number. 3/2 is a rational number. Okay, I'm going to spend a little bit of time talking about these two things and then maybe do one example to show us how this works. Actually, I'll probably just talk through these ideas and then we'll just hammer, a couple of examples in another video because these problems can get a bit long, so I don't want to drag this out too long. The linear factorization theorem is pretty helpful because what it tells us is if you have this polynomial, this is our standard form of a polynomial, right? We can always write it as the a sub n, that coefficient that we have on the leading coefficient, times x minus some number, times x minus some other number, times x minus, however many times n numbers you need to do if the degree is n. The problem is that we don't know what those numbers are, those c sub i's, c1, c2, c3. We don't know what form those take on. They may be rational numbers, like we saw in the possible rational zeros theorem, or the rational zeros theorem. They may be irrational numbers, which we don't get from that theorem, or they could be imaginary numbers. If they are something we can work with, that'll help us find the zeros. Because once we have it factored like that, all we have to do is set each of those factors equal to 0 if we're trying to solve where p of x is equal to 0, which is the definition of finding the zeros. So that's pretty nice that we can find those easily. Down here I have some steps for how we might do this. If possible, factor and solve p of x equals 0. So if you can find a way to factor it, if there's a technique that you already have for factoring, like factoring by grouping, or if it's a polynomial of the quadratic type, or if it's already factored, then use those techniques. If it is not factorable using previous techniques, we're going to do these things. First, use the rational zeros theorem to find all possible rational zeros of the polynomial. Pick one of those. So this is kind of our guess and check that we did in the previous video, where I think we picked one and it happened to work. Yay. But we got lucky there. So we're going to pick one of the possible zeros that we found in step 1 and see if it works using synthetic division. If it doesn't work, and what does work mean? Work, if I put this in quotes, which I really probably should have, means the remainder is 0, because then it divides evenly. If it doesn't work, you have to try another one from your list. If it does work, then you can factor what you are given into x minus that number times some other polynomial. That other polynomial will come from your synthetic division. Then use your rational zeros theorem again to find possible rational zeros of what is left there. And you just keep doing that until you have these linear factors, x minus a number, x minus a number, x minus a number, and one quadratic. And that one quadratic you can either factor if it's factorable, or you can use the quadratic formula on that quadratic that remains. So those are our steps. That's what we're going to work through. Pull up the next video and then you can see how we're going to work through those steps in this example.